Hello and welcome to IEEE Soft Robotics podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa ElDiwiny, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
Hello and welcome to IEEE Soft Robotics podcast. Hello, YongLae. Thank you so much for joining us in the podcast. I would like to ask you how you would like to define yourself for the audience who may be first time listening to you.
Thanks for the invitation. My name is Yong-Lae Park. I'm a roboticist, and I'm mainly focused on research in the area of soft robotics. So inside of soft robotics, I'm also interested in developing new types of actuators and sensors like artificial skins, artificial muscles, and then by integrating those sensors and actuators, so I'm building robotic systems that could be applied to human bodies or interacting with humans.
So I would like to go for your childhood. How was your childhood being interested in science and technology as a kid?
Yes, so I came to know about robots from the TV animations and cartoons. So there were two types of robots in my childhood. There were two types of robots in my mind. So based on what I learned from animations and cartoons and also sometimes books. So one type of robots is huge, strong robots. Those kind of robots protect Earth and human beings from aliens or some evil things. So that is one type of robots. The other type of robots in my imagination and in my mind is small and interactive humans. So you can play with robots, you can interact with robots, and you can also ask them to your chores. And those kind of robots were in my mind.
So when we go to the audience, one of them asked that your inspiration for designing sensors, and they are thankful for what you're doing in this research line. So maybe I just ask you about the designing process for sensor and actuation. And because in soft robotics, we speak about sometimes we have the passive material and also the active material. If we speak about ionic conductive polymer or this category. If you can tell us how it takes to design a material that could be as a sensor and actuator at the same time, and what could be a trade-off in the design process. So if you can tell us about how you design the sensors that could be embedded in the material. First step, how you do that?
So yeah, in my previous research, so we got inspiration from biology. So if you look at your biological muscles of humans or animals, so they have a sensory organs called Golgi tendon organ and muscle spindles. So they are embedded in the muscle, and then they can detect the position change and also force change. So imagine you have hundreds of muscles in your body, but you have all the muscles with embedded these sensors. So in that way, you can control the muscle, you can control your motions, and you can control your force of your body in the level of muscles, in the level of actuators. So from this inspiration, we wanted to have these kind of sensors in the actuators. So in traditional robotics, you use encoders and you use load cells for detecting position and also force. But if you have sensors that can directly detect how much displacement you are making or how much force you are making, your control will be more accurate, and you can have more adaptive motions. So in the robot. So from that inspiration, we started building sensor embedded actuators.
So if you can tell us about maybe biggest technological blocks for embedding sensor in for example, in material or your soft robot, because every guest just highlight it's still super challenging. If you can tell us about the challenging that you maybe can pinpoint what is still challenging for designing sensor itself, modeling them, or designing them, or embedding them. So.
Yeah, so robots are advancing a lot, significantly these days. But if you look at biology, so for example, if you look at just the human hand, there are thousands of tens of thousands of sensors on your hand. So you can have really dense sensory organs, array of sensors in your body. So the current robots are lacking of those sensing capability and really abundant information from the sensors. So it'd be great if we can put more sensors and more sensors in the robot body. But the problem is signal processing and how would you deal with data? How would you deal with processing all the data? And also, if we have so many sensors, you should have signal wires, so many signal wires connected to the sensors. That makes the system really complicated, complex, and your fabrication process is really difficult. So the first roadblock is adding so many sensors in your body, in the robot's body. But the second challenge is how you would process those signals and those data. And then you also need to think about how you can deal with those wires and signal bugs. So you can keep your structure as simple as possible.
That's a very interesting point. I'm curious to ask you in that case, Yong-Lae, do you think the structures, when you select the geometry or the structure, and the other side also they say that the huge computation power you have to do, is there any way to circumvent this issue? Do you think if you select a certain geometry so that you can map the sensing in an intelligent way and capture what's really you're looking for in the system? Is there any other way to do that to circumvent these issues in the design process?
Yeah, so that is part of morphological computation or embodied intelligence. So that's what soft robotics researchers want to do. So many of the researchers want to do. So if you can embed those kind of intelligence in the structures, so then you can relieve the burdens of control and processing a lot. So it won't take care of the entire control, or it will not take care of all the processing efforts, but at least it could alleviate the processing and control efforts by embedding those structural intelligence in the body.
That's an excellent point. I guess ask you in that case, do you think the representation of this sensor, because we speak about how the geometric, for example, nonlinearities or the material nonlinearities could maybe play a significant role to get rid of the controller design, for example, if we extract the beneficial geometric nonlinearities or the material nonlinearities, or maybe the way we represent this sensor in nonlinear topology in the material. Have you ever thought about that? How you can make it simpler and extract the features you already have, the intrinsic features they have for nonlinearities, for example?
Okay. So in traditional robotics, many times, in many cases, we consider the system linear. So you could have simpler mathematical models and your control is simpler. But in soft robotics, if you use polymer materials especially, then there are variations in the material properties. And also there is hysteresis in the system. So you need to take care of those features if you want to have nice models or accurate models. But it's not always easy using mechanics or physics. So one solution could be used machine learning, or some other solution could be used statistical process. So for example, in the hysteresis, you can consider your hysteresis as random process. Then you can have a stochastic analysis. Then you would have a better understanding of hysteresis and also sometimes a nonlinearity. So that is something you can take. That is one way to take care of those nonlinearity and hysteresis in the system. And but nonlinearity is not always something you need to avoid. Sometimes you can get some benefit from nonlinearity. So if you look at your body and your muscle is really nonlinear. So if you uh, so if you apply force and if you contract your muscle, and there is some point you can make the maximum force. So depending on the position, you have different force you can generate. So it's not really linear system, but that is something you really can adapt to your body to your environment. So by having, if you utilize nonlinearity, sometimes it's not easy to model and control, but there must be some benefit to it.
That's thanks for sharing that. Thank you. Yeah. And I'm curious to ask you, when you design the sensors, for example, is there something like an avoidable trade-off, something you have to, yeah, maybe to give up on this design process? Do you have something like that you still, I have to give up in this wish list, for example, I need that, but I can't get them at the same time? There's a trade-off, an avoidable trade-off in the design process.
Design process. So trade-off in design process.
Or maybe
So
after design, if you have other process in different stages, if you have a trade-off and you can't really avoid it. So
mhm. So like I said before, yeah, if you want to embed or if you want to equip the system with more sensors, and the system becomes really complex, and the fabrication process is also difficult. And then the system is computation heavy. So those are always the trade-off. So you want to have, you want to get more information from the system so you can have a better control and you can have a better prediction of the system. But the problem is the more information you get, that means the more sensors or the more components you need to put in the system. So that is always trade-off, right?
great, great, yeah. And maybe there's also arguments, but one argument. So we have seen that software robotics is pretty slow, and of course, depending on the context of the application. But what we see when it comes to, for example, any conductive polymer, or this material, this category, we have this kind of trade-off between the forces we aspire to have and the response time. There's like trade-off between the response time and the forces. Do you agree with that? Do you think how we can have maybe a reasonable high forces that can use, yeah, because still the force is pretty low, and also the response time is also maybe not slow as well. I don't know, have you ever thought about this? The,
Yeah, so I can give an example with the pneumatic actuators. So if you look at pneumatic artificial muscles like a PAMs, pneumatic, yeah. So if you look at artificial muscle, sorry. So I can give you an example with pneumatic actuators. So if you think about pneumatic artificial muscles like mechanical muscles, if you want to have a higher force generation, then you need to have a larger diameter of the muscle, which means you need to have a large volume of the actuator. So it will take longer time to put airs to generate large force. So there is trade-off. So the response time will be longer and the actuator will be slower, but you can generate higher force. So to overcome those limitations, you can make really small cells of actuators, many actuators, and those small actuator chambers can be configured in parallel or in series. So you can control your displacement and you can also control the contraction force. But each cell doesn't take long time to actuate. So if you look at only one single cell, that doesn't generate large force and that doesn't generate large displacement. But combining many cells of those actuators, you can configure the system so you can have desired forces and desired displacement.
that's excellent point. Yeah, thank you for sharing that. Yeah. And I guess ask you, what maybe you think, what area or direction you think in terms of designing the sensor or maybe soft robotics in general, you think is very promising, but maybe we still don't give much attention, or we don't consider maybe the real question. What's something you think is still missing, or maybe we don't give much attention to it at the moment? What do you think could, yeah, should looks like, or if you ever thought about, we don't really consider that point.
Mm-hmm. Yeah, I thought about that too. So in soft robotics, a lot of people use polymers. And
What?
also so in soft robotics, a lot of people use, including me. So a lot of people use polymers for the main material to make sensors, actuators, and robots. But most of the polymers are not really environmental friendly. So one point of one advantage of soft robotics is you can make the robot really cheap and simple and disposable. But if you dispose those sensors and actuators and robots many times, then I don't think that will be beneficial for environment. So in the future, it'd be great if we can create cheap, biodegradable polymers that could be used for soft robotics.
Very excellent point. Thanks for saying that. I think that's maybe one of the most interesting answers for these questions. I'm curious to ask you that case because yeah, you're right. For example, when we go for any conductive polymer, it's still toxic. And what does it take to achieve this goal? Do you think we have to maybe change something in the way we design them? If you can highlight more in more detail, if we consider that being beneficial, what will be changing and what we do? Which factor will be changing to achieve this goal?
Yeah, so far there are many options of choosing different types of polymers. So polyurethane, silicone, and even in the same type of polymer, there are different grades. So you can find very different grade of stiffness or Young's modulus or stretchability, these things. But currently in the biodegradable polymers, you don't have those much choice, many choices. So if you want to have really biodegradable sensors and actuators which are practical for different applications, then it'd be great you can have really many options of polymers with
Yeah,
biodegradability. Yeah.
right. Yeah, yeah. And I'm going to ask you about maybe what could be challenging when it comes to designing multi-material, for example, because you focus on bio-inspiration. We have a debate recently about bio-inspiration via spy hybrid design. And when you look to the solution, for example, multi-material, when you combine two different material, there's something you have to load in that case. I mean, it may become how we can make the stress concentration in the design maybe lower as much as we can. So from your experience, when you combine two different material, what's it challenging or integrate material, two material and same structure? What's really
Yeah, one big challenge is always interface between the two materials. So if we have a multi-material structures and those two materials need to bond together very well. So otherwise it will be the weak point or failure mode. So when you stretch multiple times, when you bend multiple times. So you need to think about how you can interface those two materials and then how you can make those two materials bond together really well. So that is one big challenge always we have. So for example, if you want to use some type of polyurethane, and if you want to use some type of a silicone rubber, but those two materials doesn't really bond well. So to make really good cross-link, you need to use the same type of polymers, the same type of materials. Like even though you have different stiffness, you need if you use a silicone rubber, it'd be great if you can use a different stiffness, different types of silicone rubber with different stiffness. But we cannot really use different materials to make multi-material structures. So that is one challenge if you can make those materials bond really well without failures, and then that will give us a lot more choices of making sensors and a lot of that will give us a lot of options for making sensors, actuators, and robots.
So I'm curious to ask you, what could be still maybe main challenges in your research when it comes to your lab? What's something you think is very interesting you're doing now and maybe focus for, yeah, in coming years, and you think it's very challenging as well, and also interesting for your lab. If you can tell us about more of that, the focus in your lab.
Yeah, there are many challenges, but one of the challenges we are always facing is modeling. So we want to model the system, we want to model the structures to predict how they behave. But if you use soft materials, if you use polymer materials, as I said before, because of the variations of the material properties and because of the non-linearity, it's really hard to make accurate models. So that's always challenging. So these days sometimes we use machine learning, sometimes we use a stochastic process to predict those behaviors. But if we can predict, if we can have a way to predict the behavior of the polymer materials and the soft structures, that would be really useful in the future.
That's very interesting point and excellent point because yeah, it's super challenging when it comes to designing polymer. Why you bother yourself with modeling? Because I didn't find, yeah, maybe I'm wrong, but there's no much effort in modeling this material. It's highly nonlinear, viscoelastic, and it's really complex.
Mhm.
How you manage to maybe capture what you expect? What, yeah, if you can tell us about modeling, which level of modeling you have to go for to capture this complexity in this material or expecting the behavior, because there's no much effort maybe. Yeah, it's hard, and if you can tell
Yeah,
us how you do
yeah.
that, how you manage even to get these results.
I don't know if I'm really managing those things. I always feel hard on that area.
Yeah,
Yeah.
but which level do you think you have to go for to understand them in the modeling? Which maybe parameters you look for in the modeling, so that you need to get this parameters, or you need to consider this significant element or parameters. How we
Yeah.
think
So
about this modeling? Yeah.
yeah, in solid mechanics, so if you use metal materials, so you consider most of the materials have a constant Young's modulus in the elastic region. But if you use polymer materials, your Young's modulus is really not constant. It always changes. It's really nonlinear.
Yeah.
So at least if we can predict the curve of Young's modulus or other material properties in the elastic region, then that'd be really useful. So since we don't have those kind of we don't have those kind of information, we get those properties empirically or experimentally. So it's not easy to implement or if it's not easy to uh, employ, I don't know, if it's not easy to use the information provided from the data sheet. Yeah.
Yes.
So we get those, we try to get information experimentally and empirically. Yeah. But the experimental data is not always consistent. So there's always certain, there's always, there is, there are always something that affects those experimental results in the lab. So
Yeah.
I don't know if you can ever get those information, but yeah, I really want to have those
Yeah.
uh, information about the materials.
Yeah. Thanks for sharing that. This is also hard. Yeah. So you're doing really, yeah, maybe a stride in that area. So thank you for doing that. Yeah. I'm curious to ask you whether anything you thought would work out very well, maybe in modeling, because you're really doing a lot for modeling or designing process. And when it comes to empirical work, you found something was counterintuitive or surprising result. You didn't expect this result. It's really counterintuitive. Have you ever something that happened to you when you design modeling, or maybe, yeah, before going to real experiment, the result wasn't expected, was counterintuitive to what you thought you have to see?
Mhm.
Have you ever had something like that?
Yeah, I can give an example of that. Uh, so in one of my students' research, we were building mobile robots, a new type of mobile robots. So it's shaped like a tripod. And then in each leg of the tripod robot, you have a vibration actuators. So depending on which two of three actuators you're actuating, you can make omnidirectional translational motions. So it's more like just a vibration mobile robots. So you apply just vibrations of the leg of the three robots. So there is no linkage, only just vibration. Vibration, high frequency vibration. So if you apply vibrations in these two legs, then the robot moves this way and the other way like this. So we wanted to make this robot rotate too. So we thought to make this robot rotating, we thought to make this robot rotate, we thought we had to vibrate these three actuators sequentially. So then we thought it will make this kind of rotational motions. But the problem is it was really difficult because we are applying high frequency vibration, like 60 hertz, relatively high frequency vibrations. So we just vibrated all three actuators at the same time. And we didn't think about really phase or sequence. So in the beginning, it vibrated randomly. And then at some point, it synchronized by itself. And then it started rotating. So yeah, so in that research, we were kind of surprised how we can get that kind of effect or result. But if you drop coin on the table, the coin bounces randomly in the beginning. But at some point, it starts rotating until it stops. So it was something like that. So the random vibrations of the tripod robots that physically or mechanically synchronizes it. And then they make sequential vibrations and then they make rotation. So that was really unexpected result, and then we were excited about it.
That's interesting.
Yeah. I also found the interesting article related to this vibration rotations. So actually my student. So in Manchester Museum in UK, so there is a statue called Nebsenu. So that is ancient Egyptian statue displayed in Manchester Museum in UK. And so I think this is about like 7 years ago, they had a really news about this statue because people saying this statue is cursed. So the statue is just displayed in static, but really slowly it rotates. So at some point you go to the museum and then it's facing this direction. But at some point it's facing the other direction. So people were really interested in how this happens. And then scientists did some investigations, and then they found that the vibration of the buildings and vibration of the streets makes this statue rotate because the bottom of the statue has a really slightly convex shape. Yeah. So the interesting thing is they put a camera like a few days in the museum, and they observed the statue. So during the daytime, the day starts, and then the sun rises, and then the statue rotates slowly, very slowly. And then at night, the sun goes down, and then people are not moving, and there are not many cars outside. And then the statue stops. So it looks like it's sleeping and waking up, sleeping and waking up.
That's interesting. I think that,
yeah, so you can look it up online. So there is information that's really interesting. So it is called Nebsenu. I don't know what it means in Egyptian word.
It's interesting that how the shape of the curving is really significant in design. So that's interesting. Yeah, very interesting.
Yeah, so just doing some experiments, that is really exciting sometimes in the lab. But if you find the information which is related to your research, but you never expected to have, that is really a lot of fun. Yeah. That is really a big part of your research.
Thanks for sharing that. Very interesting. Very interesting. Thank you for sharing the story. So we are close to the end. I have a few questions. I will go to the audience question. We have, maybe we can take one because it's a long question. The first question from Eric. He asked us about computer vision found widespread success with the advent of self-driving car. So do you think soft fingers and artificial tactile sensing are moving towards also commercial success, to be commercially successful? If so, what are specific application you think about?
Yeah, I think that's highly possible. So I'm doing robotics, but some people are thinking, some people who are, I'm doing soft robotics, but soft robotics is not really for replacing traditional robots. So traditionally robots were made of metals and rigid structures, but those robots have their own applications. But I don't think soft robots will replace those areas. So by having soft materials and soft robots, I think we can find new applications in which robots were not really used in the past. So by developing soft robotics technologies, so I expect we will have robots in our daily lives where we didn't really think about we were going to use robots. So, yeah.
Interesting.
Yeah. So 20 years ago, I never thought about computer speaker will be your friend in your home.
Yeah.
Yeah. But now everybody calls your speaker and then ask a lot of information and ask your ask a lot of things to your speaker. Yeah.
And also, Eric has a message for you. You say that as a PhD student working with liquid metal embedded soft sensor, I must thank you for all interesting reading you have provided. So he won't say that as well. So thank you for that.
Thank you.
So because we're closing the end, maybe I'm asking you, do you have any crazy questions or me ideas you have for when it comes to sensor and actuation? Do you have any crazy ideas you ever thought about? Or when you look to nature, do you have any inspiration you think that's very inspiring and we don't really consider that? It's not optimum, but that's what exists in nature and that's interesting.
Yes, so that reminds me of my PhD topics during my PhD research. So my inspiration for my PhD research topic was arthropods, like scorpions and insects and crabs. So when you think about robots and then when you think about future robots, and then relations to biology, it's easy to think about advanced biological organisms like humans and mammals. But not many people think arthropods could be really useful. I know. Yeah, so it is easy to think about humans or mammals as a model of robots. But we focused on arthropods like scorpions and crabs because they're covered with exoskeletons, and it's easy to think exoskeleton don't have sensory feedback. But we found interesting sensory feedback organs in their exoskeleton called the Sleeve sensilla or campaniform sensilla. So by having those sensors, they can detect the structural deformation of their body. So it's more like a biological strain sensors in their bodies. So we wanted to have those kind of structures in the robots. So even though you make robotic structures with rigid materials, if you can have those strain sensors, many strain sensors spread on the body, then you will have a sensing capability like human skins. Not exactly the same way, but similar information you can get, like the location of the contact and also the magnitude and direction of the content.
Mm-hmm.
So during my PhD research, those arthropods were really inspiring to me.
So I'm curious to ask you about the risk and ideas, because we ask all the time about having risky ideas, new ideas. Sometimes it's challenging in terms of getting like publication or funding, various incremental research. For you, how you manage to get maybe innovative ideas and maybe risky, and have you ever thought about this kind of, because we have a pressure of publication, and people say that sometimes if you have a pressure to publish, you're afraid to go for risky ideas because it's risky. Have you ever thought about the risky ideas? If you have an idea, I want to do that, and also it's risky. Have you ever thought about this risk in what you aspire to design?
Yes, so so we have many ideas, but not all the ideas are really working, and also not all the ideas are appreciated by other people, right? So sometimes we try to publish a paper based on our ideas, which we thought really interesting and exciting, but there are also many papers which were not accepted. Yeah. So I don't know. There is a really specific way to manage those situations, but you just try, and then you just try, and then you just try to persuade. Yeah. So
Yeah.
that's what you do. And also, I think a person, I think, yeah. And also, we cannot generate new ideas all the time forever, right? So our capability is really limited all the time. As a just uh, just a simple human, and also I don't have a lot of ideas all the time. Yeah, sometimes I have ideas. Sometimes I feel I'm really limited to certain areas. So what I try to encourage my students to generate new ideas. So
Yeah.
the way I think is really different from the way other people is thinking. So each person has different way of thinking. Each person has different way of perspectives in designing, controlling, or making robots or other things. So I always ask my students to generate new ideas, and then if you have very interesting ideas, go for it, and then I'm always supportive. So many of the papers published from my lab was initiated from my students, not from me. So I think encouraging other people and encouraging new ideas is really important, and that makes the society always growing and developing.
That's a very important message. So thank you for saying that. Thank you. And do you think ego is important for you?
I think you need a balance.
Okay.
Yeah, so ego is important because that is sometimes energy to generate new ideas and then propose new things all the time. But if your ego is too strong, then you will lose chance to look at other people's ideas, other people's work. Yeah, so you have to respect and you have to accept other people's ideas and other people's work. But but you need to think about what you want to be and then what achievements you want to have. So to make it possible, you need to have egos, I think. Yeah, but that's a really philosophical question. Yeah, it's hard to answer.
Okay, I appreciate the honesty. Thank you for that. Yeah. And what could be the most important quality you have gained and you have to maintain in academia? Something you have to maintain, most important quality for you.
So uh, always, so based on the area of my work, so like I said, idea is really important. So you need to generate new ideas and novel ideas all the time. Yeah, but idea doesn't really come suddenly. So I don't think I'm a really smart person or I'm smarter than normal people. But sometimes if you think about one thing long time continuously, if you focus, and then sometimes it takes time, but at some point you will have new ideas. So there are many ideas you can generate, but sometimes you need to just keep holding on one idea and then try to advance those ideas. And then you will always have some hurdles and problems. But if you think about one problem all the time, then sometimes you will have small answers and small answers, and those answers will be integrated and be a final solution.
Wonderful, yeah. And lastly, what was the best advice was given to you and was life changing? The best advice was given to you.
Yeah, so during my PhD, so I was working on developing a sensing system. So in the beginning of my PhD, and then so I was working on the part of the project. So we wanted to develop robotic sense. We wanted to develop new type of force sensor for mobile robots, and so there was a deadline for the project. And then I worked really hard, and then I spent a lot of time. And then I thought I worked really hard, but in the end, it didn't work. My idea didn't work, even though I spent so much. I spent so much time on that. And then uh, after the project, after the deadline of the project, my advisor came to me and then told me, so I understand that you worked really hard, and but PhD research is not just working hard. So the research is more like you create your own problem and then you give your own solution. So you always need to think about what problem you are trying to solve and what problems you are making. So from the time, I always thought about what kind of new problems I wanted to solve. So I think that is really great advice. And then
That's
that, yeah,
that's a brilliant advice. Even in life, I think in research in life, it's same. So that's excellent advice. Thanks for sharing that as well. Thank you. And do you have any final words you would like to say for the robotics community? Any final words?
yeah. I really appreciate this opportunity and thanks for inviting. And yeah, there are more and more people who are working on soft robotics research. So yeah, so like my advisor said to me, yeah, I want you to say to new students and the new researchers that uh, it'd be really helpful and useful if you can think about what kind of new problems you want to solve before trying to providing new solutions. You need to define your problems first.
Absolutely. That's really wise words and also beautifully said. So thank you. Thank you once again, Professor YongLae. It was a pleasure and honor to have you on the podcast. I really enjoyed it. Thanks a lot for being here. Thank you.
Yeah, thanks so much for having me.
Thank you.